Hi everyone, welcome back from break. In this video, I'm going to go over parts of Lecture 5 very briefly because it will help you with the readings this week. The readings this week are a little bit more difficult, and since I can't be with you in class, I thought this would be a good way for me to give you that extra help that you might need. So please make sure to watch this whole video. It shouldn't be that long. So if you remember from the lecture in class, we talked about populations versus samples. A population is the entire universe of cases that we could potentially collect data on. So for example, if we were interested in collecting data on voters' intentions in the 2020 US presidential election in November, our entire population would be the voting age population of the United States. Now, clearly, we can't collect data on every voter in the US. That would be impossible and incredibly costly. And almost every statistician, every researcher faces this problem where it'd be great if you could collect data on every single case, but you just can't. It's just not possible. So in statistics, we use samples instead. And a sample is a subset of the population, a smaller portion of it. So basically what we do is we take the information from our samples and apply that information to the entire population. So let's say we wanted to know what the average height of 18-year-old boys are or 18-year-old teenagers, are in the US. What we could do is we can't collect data on this for every single 18-year-old male in the US. So we could take a subsample of 18-year-old males, maybe perhaps 1,000 males, take their heights and then find the average, and whatever average of that that sample was, we would apply it to the population. We would say, okay, we know that in the sample our average was this number. The average of the population is probably close to that number. So one of the ways we do that is with confidence intervals. So let me go up here. So in the previous lectures, I showed you how to calculate the mean of a sample. The problem with using a mean of a sample is that our mean of our samples aren't always going to be exactly representative of the population mean. So let's say, for example, I calculate the average height for 18-year-old males, and let's say it was 5'10". It's possible that that's close to the real average, right? But the true population average could be 5'8", right? So, and statisticians know this. They know that the means that they calculate from their samples aren't always going to be representative of the true population mean. So instead of creating these, they're called point estimates, it's a very specific number, like the average height of 18-year-old males is definitely 5'10". Instead of saying that one specific number, they create confidence intervals around those numbers. So what they do is they create a lower bound and an upper bound, and they say that they have 95% confidence that the true mean lies between the lower and upper bound. So, for example, let's say we have some variable where in the sample the confidence interval for the mean was 11.1 to 47.7. What that means is that we think that the true mean, we have 95% confidence that the true mean is between these numbers. So that means that the mean could be as low as this, it could be 11.1, or it could be 47.7, or any number between that. So instead of being very specific about what those means are, we're giving a range, okay? So I just want to show you something, why this matters. So we could take this one step further and compare the means of two subsamples together to see if the means of the subsamples are different. So let's say, for example, I created this ideology measure where it goes from 1 to 7, and 7 is very conservative and 1 is very liberal. And let's say I did a poll and I asked Democrats, so they'll be in the blue, and Republicans, who will be in the red, where would you put yourself on this scale, right? And so I would expect that Democrats are liberal, so they would probably put themselves down here, and Republicans are conservative, so they would put themselves up here. So what I would do is I collect that data, and then I would make a confidence interval around the mean of, let's say, Democrats. And let's say the confidence interval says that the mean is anywhere between 1 and 3 for Democrats, and the mean for Republicans is anywhere between 5 and 7. So what that actually means is that Democrats could be have a mean of 1, 2, or 3, and Republicans could have a mean of 5, 6, or 7. What this also tells us is that what I could say is I have 95% confidence that the means of these two subsamples are different because they don't overlap, right? So there is no, in this scenario, there's no situation where the mean of sample 1 could be similar to the mean of sample 2. They are different. They're distinct, okay? But let's say alternatively, let's say instead of the confidence intervals looking like this, they look like this, right? And so the mean of sample 1 could be 1, 2, or 3, and the mean of sample 2 could be 3, 4, or 5. Now the confidence intervals overlap. They overlap now. What that means is that it's possible that the mean of subsample 1 is 3 and the mean of subsample 2 is 3. That is a possibility. And because of that, I can't say with statistical confidence that the means of these two subsamples are different. Okay, so that's one of the useful things about confidence intervals is that we could divide our data into two subsamples and see, okay, is this mean different than this mean? Yes, in this scenario here it is, because they don't overlap. There's never a case where they're both the same. Whereas in here, there is a scenario where they're both the same number 3. So going back to the lecture, we can also apply this to surveys. So the way confidence intervals work in surveys are a little bit different. You'll see the term margin of error there. It's just a slightly different technique, but similar concept. Basically, a survey researcher could go into the public and ask people how they intend to vote, and then they can calculate the vote shares for candidates and predict who's going to win an election. But they put confidence intervals around those predictions. So just to give you an example, let's say one survey researcher, let's just say Gallup, for example, found that 50% of the voting public intended to vote for Trump in the fall with a margin of error of plus and minus 5. What that means is that we have 95% confidence that anywhere between 45% and 55% of voters support the candidate, would support Trump, right? Because plus 5 would be 55, minus 5 would be 45, right? So what we could say is we cannot conclude with confidence that Trump will win the majority of the vote, right? He could get 45% of the vote, or he could get 55, or anywhere in between, okay? And what that would mean is that, you would compare that to the other candidates. Let's say it's Joe Biden. If Joe Biden's percentages overlap with these numbers, then that would mean that we don't know who's going to win the election. But if they don't overlap, that means we could conclude with confidence that one is going to win over the other. And you're most likely to see them overlap at the national level because the American voting public is generally split at the national level. But when you start looking at states like Idaho, clearly the Republican's always going to win Idaho. Confidence interval will be way above for the Republican, will be way above the one for the Democrat. But then in places like California, you get the opposite, where you're going to see the Democrat clearly having a larger their confidence interval will be much greater than the confidence interval of the Republican.